Welcome back. This is our next video lecture, and it is covering content in Chapter 7, Section 4, work done by a spring force. So what we're going to start with here in this section is describing how a spring force behaves, because that's one of the most important forces in physics, for many reasons that we will be touching upon. First, let's just show what we're talking about here. Right? A spring. This is an example of one of many that the department owns. These are fabricated by various companies under specific conditions, and it's just in this case, closely spaced coils of metal, right, with loops on the end for hooks. And as you know, you can pull a spring and stretch it. But springs have the interesting behavior, because of the way they're formed, that the more you pull it, the harder it gets to pull it more, right? It gets harder and harder and harder and harder. And you can pull too hard and break them or damage them, which we don't want to do. But the bottom line is that if you want to stretch a spring, the more you want to stretch it, the harder you have to pull. And if I have it at a certain stretch and I want to pull a little bit harder, I got to exert a certain force. But if I start with already a greater stretch, I got to exert an even greater force for a little change. Okay? The more you stretch it, the more force you need. That's really, turns out, a really important phenomenon in physics. And the spring is the classic example of that force, although many things behave similarly, we will learn in physics. So it's worth understanding the force that such a stretched spring exerts, and what's the mathematical formula for calculating such a force. I will add, by the way, that this particular spring that I'm showing you is manufactured specifically such that it can only be stretched from its what's called relaxed length, which is this. You can't compress this, right? The coils are right up against each other, the way this is fabricated. You cannot compress this spring, you can only stretch it. And that's true for most of the springs in our department. However, there are certainly springs, depending upon the way you make them, that can be either stretched from their so-called natural length or equilibrium length, or compressed. And I will say that all the springs that your textbook assumes and talks about and puts in homework problems are the kind of springs that can be both stretched and compressed. Just be aware of that. Okay? All right. But first, let's just describe mathematically the behavior of what's called the spring force. Historically, the mathematical formula describing a spring force is known as Hooke's law, named after Robert Hooke, an English scientist who was a contemporary of Newton, and the two were bitter rivals. They couldn't stand each other. Nevertheless, Hooke was one of the first to write down the mathematical formula that describes this force of a stretched spring. So we call this formula Hooke's law, but it's just a formula for calculating a force due to a spring. Now, the picture I'm going to show you, the diagram, is pretty much the standard scenario that the textbooks use. Okay? All right, so what we have is a horizontal surface, which we're going to take to be an x-axis, and then a vertical wall. And at one end of the vertical wall, we're going to connect one end of a spring, right there on the left end. Okay? And then the spring's going to go horizontally without actually touching the floor and be connected at the other end to a block. Okay? As far as we're concerned, this surface we are going to take to be frictionless. I mean, we know how to deal with the frictional force, it's true, but let's just not add that complication right now. Let's just deal with the spring force. Okay, now, I've marked on there a location on the x-axis that I have chosen to be the origin, x equals 0. And I have chosen it very deliberately, calling it the equilibrium location. What do I mean by that? I mean that if you let the block and the right end of the spring rest at the place that we've marked as the origin, then the spring will be at its natural length. The length it was fabricated to be at. Because when any spring is at its natural length, neither stretched away from its natural length nor compressed away from it, it will exert no spring force on anything. Okay? So we call that the equilibrium configuration. So if I sketch that over here to the side, right, with the x-axis going to the right, x equals 0 is like that, then I'm talking about a scenario where the block would be resting at that origin, and then the spring is tied like that. And if we're in that situation, we are in equilibrium. And that block will just sit there. The spring is neither stretched nor compressed away from its natural length. It doesn't exert any spring force whatsoever on the block. So there is no force on the block, so the block will just remain at rest. We call that equilibrium. Of course, that's pretty boring. It's more interesting if the block is moving, right? So some way or another, we're going to get the block away from equilibrium. Maybe we'll just reach in and pull the whole thing to the right, or push it to the left, right? So the picture that is drawn here shows the block that's as it's been pulled to the right, away from equilibrium. So I'm going to denote a horizontal vector. It's right here, maybe hard to see, with a blue arrow, and that's the displacement of the block from equilibrium, right? And we denote it delta x. And it does have a direction. In this case, it's to the right, which is plus x. So delta x is positive. Okay, now if you get the block to this configuration, maybe by pulling it out there, the spring is now stretched away from its natural length. And the spring, when stretched away from its natural length, will exert a force on the block to try to bring the block back to equilibrium. That means the spring force in this case would be to the left. And that's what this green arrow pointing to the left is. And it's labeled there F sub s for spring force. Okay? So the spring force is always trying, in this setup, the spring force is always trying to bring the right end of the spring that's tied to the block back to equilibrium at x equals 0. So if I pull the string by pulling the block to the right, the spring force is to the left. Now the picture doesn't show it, but I could imagine pushing the block and spring to the left, thereby compressing the spring, then the spring force would be to the right. Because the spring force is always trying to bring the block to equilibrium. It's an example of what's called a restoring force. It's trying to restore equilibrium. So the way we denote what's going on here is and this is the formula that Hooke deduced from experimentation, the formula for the spring force in this one-dimensional case is written in this form right beneath the picture. F sub s, the spring force, is proportional to the amount of stretch or compression. It's proportional to delta x. So we really ought to start by just writing something like that. That's the proportional symbol. Spring force is proportional to the displacement from equilibrium. That's all I mean by that is what I said earlier. The more you stretch a spring, the larger the spring force. And it turns out that for these simple springs like this that obey Hooke's law, the size of the spring force is directly proportional to the amount of stretch or compression of the spring. However, an important point, the direction of the spring force is always opposite to the direction of the displacement. Look at the picture there. The displacement of the block is to the right. Delta x is to the right, but the spring force is to the left, trying to get the block back to the left. If I had compressed the spring and pushed the block to the left, then delta x would be to the left, and the spring force would be to the right, trying to get back to equilibrium. So this minus sign is very important in the formula for the spring force, because it says that F sub s, the spring force, is always opposite in direction to delta x, the displacement from equilibrium. And the proportionality constant between F sub s and delta x is this symbol here, k. That's just a proportionality constant between F sub s and delta x. And that symbol k is called the spring constant. And it is a number that describes any given spring based upon how that spring was manufactured. Okay? Now, let's talk more about that spring constant. First of all, what are the SI units of the spring constant K? Well, just look at the formula for the spring force. Okay? This formula right here, which, by the way, is called Hooke's law. But it's just a formula for the spring force. And let's think about the units. The unit on the left, since it's force, is Newton. The unit for delta x, since it's displacement, is meter. So what must be the unit of k such that k times delta x has units of newtons? Unit of k must be Newton divided by meter. So that when k is multiplied by delta x in meters, I get a number in newtons, right? Okay, so the SI unit of this constant k, called the spring constant, is Newton per meter. Not Newton, but Newton per meter. And of course, here's a simple way to think of what k is telling you about a spring. A larger value of k means a stiffer spring. A larger k value for a spring means it takes a larger force to stretch it a certain amount. So very stiff springs have a large spring constant and therefore are hard to stretch. All right, here's a tip to always remember. I've said it already, but it's worth emphasizing. The spring force, F sub s, and the particle's displacement from equilibrium, delta x, are always in opposite directions. Okay? Like I said, if the displacement's to the right, the spring force is to the left to try to get back to equilibrium. If the displacement's to the left, the spring force is to the right. Now, here's one way we can simplify the mathematical formula for Hooke's law, which is the way most of the books will do it, including ours. But it does require one assumption. As long as the equilibrium location is at the origin, you can change F sub s equals negative k delta x to simply F sub s equals negative kx. Because the delta x, in the original way I wrote Hooke's law, means displacement from equilibrium. If the equilibrium location is the origin, then it's the displacement from 0, delta x just means x. But be warned, there's no law of physics that says that the equilibrium location, like in my picture on the right, has to be the origin. I could decide to pick my origin on my x-axis maybe over here at the wall. And then this place right here, whatever this distance is, maybe that's 1 meter. That's the equilibrium location at x equals 1 meter. Equilibrium's not at the origin now. This is the formula you still use. Spring force is negative k times displacement from wherever equilibrium is. However, most textbooks will say, well, at least for horizontal motion, like we're showing here, might as well make things a little bit simpler and choose equilibrium to be at the origin. Or choose the origin to be at equilibrium, I should say. So then you can write Hooke's law just like that, slightly simpler form. F sub s equals negative kx. That is how our book will tend to write it. Let me emphasize something. This is our first example, the spring force, of what is called a variable force. Okay? The spring force is what we say in physics is a variable force, i.e. not constant as a particle moves. So if I have a particle connected to a spring, like this block, and I'm letting this particle move back and forth on the x-axis with this spring connected to it, then the amount of stretch and compression in the spring is changing, and Hooke's law says that the size of the spring force is changing. The spring force is variable. It's changing as the particle moves. Spring force is not a constant force. That's going to cause us a little bit of a headache soon here. That we're just going to have to deal with it because the spring force is really important. Okay, what I want to do next is a little more practice with the spring force, because although it's mathematically, and I think conceptually more or less straightforward to write down, it still takes a lot of practice to get used to. So I want us to do some practicing together. And let me do something that a lot of the textbooks do in homework, but don't talk about in the actual book itself. And that is going from a situation like you see here, where the spring and the object are horizontal, or the spring is horizontal and the surface is horizontal. Let's imagine a vertical spring. Okay, so now I'm imagining something like this. There's this spring again, but instead of having it stretch horizontally, I'm going to hold it vertically. And nothing much happens when I don't have anything on it. But if I put a mass on it, certainly the spring stretches, but now the stretch in the spring is vertical. And of course, the reason the spring stretches is because the downward force of F grav acting at this bottom end on the mass hanging there. So let's talk about a spring that obeys Hooke's law, but is being stretched vertically, because now the gravitational force becomes an important player in the game. And I'm going to do a kind of a mini example. I'm going to have us go through it together. Here's the scenario we're going to consider. Somebody has mounted onto a vertical spring a pointer, okay, and at the bottom end of the spring, and put beside it a scale marked in millimeters. Okay? And now we're going to put 3 different packages hung from the spring, one at a time, as shown in the figure. So let's look on the very left here, right here. Let's call this case 1. In case 1, somebody has hung a package. It has a weight, that means m times g, value of 110 newtons. Now that's not what this is, but the point is that we've put a package on the bottom of that spring, and it's supposed to just be hanging there at rest in equilibrium. Okay, like that. Case 1. When we do that, the pointer at the bottom of the spring points to the value 40 millimeters, based on the way this scale has been positioned. All right, case 2. Take away the first package, and now carefully attach the second package onto the same spring with the same pointer and the same scale, and let them come to equilibrium where everything's at rest. And now you discover the pointer points a little bit lower on the scale to a point marked 60 millimeters. And that the weight of this package, m times g, is 240 newtons, right? It's a heavier package. And then case 3 is an unknown package. That is to say, a package of unknown weight, w. And the pointer points to 30 millimeters on the vertical scale. That's the lowest reading of all of them, isn't it? That's the information we're told about this spring and this apparatus. So here comes the first question. Which mark on the scale will the pointer indicate when no package is hung from the spring? Let's draw a sketch of that, okay? Let's say no package hanging. The spring is still attached at the top to some kind of a ceiling. I'll draw it like that. Put the little end there for connecting something to, but there's no connecting. There's nothing on it. And then here's the little pointer, like so, fixed to the spring. And then here is that scale. in millimeters. Right? It's asking in part A, what number on that scale is the pointer pointing at? I'm going to call that, I'm going to think of this, since it's vertical, I'm going to think of this as being along a y-axis, this scale. I'm going to call this a y position. I'm going to call it y0. That's the equilibrium. Well, I'll say it's the no stretch. No stretch y location for the pointer. Okay? Like that. And in part A of the problem, we are to find what that y0 value is. Okay, well, what I recommend we do is we use case 1 and case 2, where we know the hanging weights and we know the pointer values on the scale. And those two cases should enable us to get enough information to answer part A. I'm going to go ahead and push this on up so I have some room. And let me draw some free body diagrams. Well, let me draw some full pictures. Let me draw case 1. Okay, which is, I'm just going to refer to the picture right up above, right? There's case 1. Now somewhere above, so I'm going to call this y value here at 40 millimeters. I'm going to call it y1. Okay, the y location of the pointer when it's hanging there at rest in case 1 in equilibrium is 40 millimeters. And the thing, remember, that package there in case 1 is hanging at rest. It's in equilibrium. So the net force on it must equal 0. Let's draw a free body diagram for it. The package in case 1. Okay? Think of the package as a particle, a dot. Then there would be, would there not, be F grav 1 vertically down, and there must be an upward force to balance it, acting on the package. It comes from the spring that's connected to it, right? And the spring is trying to get back to equilibrium, so there's a spring force, Fs, that in this case is vertically up. See my free body diagram for that first package? Package is hanging at rest in equilibrium, no acceleration, net force must equal 0, so F grav 1 down, and the spring force must balance. So now I apply Newton's second law to that package. A sub y equals F net y over the mass of that package. I'm going to call it M1. Well, the good news here is that A sub y is 0, right? The package is in equilibrium, it's not moving. So F net y must equal 0. Net forces must balance. Well, that means F grav 1 must equal F spring. Yes? All right, let me scoot this on up a little bit so I have some room to write. Okay, now, magnitude of F grav 1 is M1 times G, but that's what we mean by the weight. So I'm just going to replace the magnitude of F grav 1 with a symbol W1, where W1 is just what we mean by the weight of package 1. And I know that number, when it comes time to plug in numbers, it's 110 newtons. Now that must equal the magnitude of the spring force. We use Hooke's law, okay? We're going to use Hooke's law for this. And the magnitude of the spring force, based on Hooke's law, is given by the spring constant, little k, for this spring. It is just a property of this spring, times, now be careful, the magnitude of the displacement from equilibrium. Well, I really ought to say from no stretch. The magnitude of the displacement from no stretch. Right? A spring is all about how much you stretch it or compress it. So my first picture shows, well, it doesn't show it lined up terribly well. I could have done a better job, I suppose. But on my scale over here, somewhere above y1 is the line y0, where the pointer would be if nothing is hanging on the spring, no stretch. That's what y0 is, where the pointer is when the spring is not stretched. But in this case 1, with package 1 hanging on there at rest, the pointer's now down lower at y1. So how much has the spring been stretched by? That's what's important. The answer is y1 minus y0. So, bringing this back up, what I write here is k times y1 minus y0. That's the amount of stretch in the spring. Let me number that equation. 1. All right, now I want to talk about case 2. That's not enough information, you understand, because there are two unknowns. There is the unknown, whoops, I wanted that to be red, sorry. The unknown value of the spring constant and the unknown value of y0. So I need another equation. Well, that's why they give me two cases. Now let's look at case 2, where the object hanging at rest at the end of the spring has a weight of 240 newtons. Right? And now we're at the location here that I'll mark, y2, 60 millimeters. But remember, somewhere up here is y0. And I want that, because how much is the spring stretched in case 2? y2 minus y0. Yet the block is in equilibrium, so there's an F grav Fg2 down, and there's a spring force of equal magnitude up that balance to satisfy Newton's second law. So now let's apply Newton's second law to case 2. When y2 equals 60 millimeters. Well, you still start from ay equals f net y over m. Now it would be m2. ay equals f net y over m2. But again, the assumption is that the package is just sitting there, hanging there, I should say, at rest with no acceleration. So f net y must equal 0. So the downward gravitational force magnitude must equal the magnitude of the upward spring force in this case. I'm going to call the magnitude of Fg2 the weight of the package in case 2. I know what that is, that number. It's 240 newtons. And on the right-hand side, I use Hooke's law. The magnitude of the spring force is the spring constant for the spring. That is a property of the spring. You can't change the spring constant by putting different masses on the spring. And then I multiply that by the amount of stretch of the spring. That's y2 minus y0. I'm going to call that equation 2. Now that's a second equation with the same unknowns as the first equation. So now we have two equations and two unknowns. We can do our algebra. So what I'm going to do is get rid of the unknown I don't want, k. I'm going to do that by just taking from equation 1, and solving it for k. K equals w1 over y1 minus y0. And then I'm going to substitute that expression for k into equation 2. Right there. Let's see what we get. W2 equals k. W1 over y1 minus y0, then times y2 minus y0. Let me write that as w1, just do some grouping, times y2 minus y0, over y1 minus y0. Now, I still have to do all the algebra to solve this expression for y0, but that is the only unknown. So I'm not going to go through that algebra. You should practice for yourself and convince yourself you can do it. I'm just going to write down what you get for the formula for y0. Okay? Note carefully. It's the weight W2 times the pointer value y1 minus the weight W1 times the pointer value y2 over W2 minus W1. That's what you get. Now I'm going to put in numbers. I'm going to leave the y values in millimeters. That's going to be okay, as you'll see. That will just give me the y0 value in millimeters. The w values are weights. That's the magnitude of the force due to gravity. That's in newtons. So for W2, 240 newtons. For y1, 40 millimeters. Minus W1, 110 newtons, times y2, 60 millimeters. All divided by 240 newtons minus 110 newtons, which is 130 newtons. The unit of newton cancels between the numerator and the denominator. You get a number for y0 in millimeters. If I round it to 2 sig figs, it's 23 millimeters. If I keep an extra sig fig, it's 23.1. So that's where the pointer will be, with no mass hanging on it. And of course, my sanity check is that it has to be above case 3, because that case 3 clearly is the highest location of the pointer in the 3 cases, but there's a mass hanging on it. If there's no mass hanging on the spring, it's got to be higher than 30, so I know it had to be less than 30 millimeters. Turns out it's 23 millimeters. Okay? Very standard kind of thinking that you have to do with a spring, at least a vertical spring. We're going to do a lab experiment later on in the semester where we are exactly going to do this kind of thing. We're going to hang a mass from one end of a vertical spring, allow it to come to equilibrium so that it hangs at rest, and read off its location on a meter stick that sits standing vertically beside it. So this is good practice. Let's go ahead and finish part B of this example. What is the weight W of that third package in case 3? Okay, well, we still have a package that's in equilibrium, so there's a downward gravitational force, I'll call it Fg3, that is balanced by an upward spring force, F sub s. The acceleration is 0, so the net force must be 0 in this case. I'm going to need to get myself some room here. So let me do that right here. Just get myself some room. Okay, so now I'm doing case 3. A sub y equals F net y over m3, but a sub y is 0, so I'm just at this F net y equals 0. So the downward gravitational force on package 3 must equal the upward spring force. So W3 for the weight, or since they just call it W, I'll just call it W. That's the unknown weight of package 3, must equal the magnitude of the spring force from Hooke's law. That's the spring constant times the amount of stretch, which is y3 minus y0. And now I'm just going to take my expression for k that I had from equation 1 and substitute it into this k now. Okay, so W equals W1 over y1 minus y0 times y3 minus y0. Or, let me come down here and write it. W3, or W, equals W1 times y3 minus y0 over y1 minus y0. And so the W1 was 110 newtons times y3 is 30 millimeters minus y0, let me use the extra sig fig, 23.1 millimeters, over y1, 40 millimeters, minus y0, 23.1 millimeters. Notice all the millimeter units cancel. And I'll just have units of newtons, and I just go to my calculator, and I see what I get. I get 44.9 if I round it to 2 sig figs. That's 45 newtons. Well, it definitely should be less than 110 and 240 because it's not stretching the spring as much as those cases, right? So 45 newtons seems reasonable. Okay, so I've introduced to you the spring force. The spring force equation is called Hooke's law. I talked about it in a horizontal scenario and in a vertical scenario. We're going to be doing a lot of practice and a lot of use of Hooke's law. And what I want to do in the next video lecture, which will be part 2, is I want to talk about how do you calculate work done by a spring force. It's complicated by the fact that the spring force is variable. As a particle moves and a spring stretches more or less, the spring force changes. So we don't know how to calculate the work done by a variable force. We're going to have to come up with a whole new method. And that will be the next video. That's all for this video.